Awesome. Thank you so much. And thanks for Carl for giving away my punchline already at the end. Um, so um, I'm Marie Henderson. I'm a postdoc at Goddard Space Flight Center, and I've been working with Zach Morse, Dan Cremens, and Jose Hurtado to start looking at potential lunar icy simulants with the Artemis baseline camera. And so this is a pilot project that got a very small amount of money just to start to try to work on this issue. And so just going to give you some preliminary what we've done and hopefully find some way to do more in the future. And so this research started in an ice cave in Iceland. And we went into this ice cave and I tried to take some pictures. And as a person who spent a lot of time working with imaging science and working on missions like that, I said, why are my pictures horrible? I can't see anything. And that made me start asking a lot of different questions. How are cameras actually going to attempt to image different types of ice on the moon? And so we're going to use a couple terms during this talk, which is our cryolithology, which is the study of the genesis structure and lithology of frozen earth materials, and also the cryostructures. And so that's the textures that you see with an icy regolith mixture. And so a lot of the ice that's on the moon, Mars, and these other small bodies, it's really poorly understood. And so we want to start to analyze multiple different cryolithologies and their expressions to increase the science return that we can do. And so since one of the leading science objectives from the Artemis 3 science definition report is to understand the character and origin of these polar volatiles. And so this is a really great figure that Carl also showed, showing all these different cryolithologies that could exist, where you actually have ice within these grains, you could have ice coating these grains, you could have icy matrix, or you can have these massive ice or ice structures within them. But when you start to think about every single one of these, there are now different observational constraints that each one of these would actually would lead to. And so if you have a clean ice that's just pure water ice, you're ending up with something that has a really high reflectivity and all these lighting and you have to spend a lot of time thinking about your lighting angles and the way that your lights from maybe astronaut suits or different missions are actually going to hit that ice. But if you have a dirty ice, then we have the exact opposite problem where it's very dark and you need to think about exposure. And so it can still also be reflected and affected by those lights. But there's a possibility where we have some stratification where you're really going to want to capture both things that are really bright and really dark in a single image. And then the ice matrix conglomerate. You're going to need multiple exposures to probably capture all the pieces in there and also different imaging angles to capture the angularity of anything that is within that matrix and to truly try to get at what is the matrix and what are all the class of. And the ice cemented regolith, which is probably most likely what we're going to see, but the ice grains could be very small, very discrete, but these textures that may be prevalent on the surface could be revealing of different properties. But so coming back to the AOA SAT, there's a really great line in here that I really want to put forward that where our efforts are encouraged to exercise the capabilities of the cameras similar to those baseline for Artemis in lighting conditions similar to low lighting environments thought to be in the PSRs. So that's what I tried to do. So we bought the Artemis baseline camera. We got the Nikon Z9. It's a 48 megapixel mirrorless camera. It's been designated the Hulk. So when you see that wording out in the world, that is what this Nikon Z9 is. They have used this camera on the International Space Station. They've used it in the recent analog test for JET. You see it there being held by the astronauts, and the Z9 just arrived to the space station for testing in January of this year. And so what we wanted to do was to try, like I said, we didn't have a lot of money. So we wanted to test these imaging conditions of different cryolithologies on the smallest scale that we could achieve with what we had. And so we developed a small freezer laboratory investigation. And so we wanted to combine a LiDAR instrumentation with the camera measurements and to attempt to differentiate samples that have different amounts of water ice included in them. See if we can find any differentiation when we're combining LiDAR and visual imagery. So we made a bunch of samples. And so we prepared these icy regolith samples, and we made a couple of different concentrations trying to get at what we may see, which is we did a clear water ice. We also did a dry. This is oh my goodness, OB1A, that's the name of the simulant. OB1A simulant. So we did dry, and then we did a 3% weight percent water, a 5.3 weight percent water, which some of you may be able to relate back to the L-Cross mission, a 6 and a 12 weight percent. Then we also did a pure water ice sample as well as a dark ice sample. So we took, for the dark ice, we did a JSC1A, put in like 20% of water into that, and then we made a like a mixed sample that was the dark sample with a bunch of larger class in, with maybe some dry simulant on top. We just sort of threw the gamut into a tiny pan. And so we followed the preparation within Atkinson 2020, and then we were able to freeze all these samples in the Goddard freezer lab. And so what we did was we tried to take images from multiple distances, one further away, as you assume the astronauts would take as they approach, one closer up going straight down from about waist height. And then we did attempt to do, if the astronauts could bend all the way down and get a close-up image using this camera, that is what we wanted to emulate as well. And we also attempted this with two different lighting conditions. We did a low angle and then also diffuse lighting from above. And then we followed that up with some LiDAR observations of all of these samples together. And for our photographic sequencing, we followed this bracketed exposure shots, which is what they're using in analog tests such as JET, and they're starting to plan to capture the dynamic range that you may see during South Polar observations.
1 minute left.
How many? One.
Perfect.
So our LiDAR observations were inconclusive. And so I think part of that right now, looking at it, is that we were not able to reveal that trend. And there's probably some inconsistencies due to the constraints of the test that we built. These depth of pans were probably not deep enough, and the color of the regolith seemed to be influencing that more. And it really goes to show that a more comprehensive with larger scale, so this isn't a great shot at all, but we would need a more natural environment there. But when we actually got to imaging with the camera, as Carl had alluded to, you really can't tell the difference between these different amounts of water ice, especially in these lower amounts that are similar to orbital observations. And so we were able to see that the focus that we could get was very consistent in the center, but we did start to lose focus as we go out with the current lens setup that is being used in certain analog tests. We did start to see that the textures did become really well revealed there, and that we needed a focus stack to even capture the dynamic range or the depth of field that we have in this mixed sample. So just some really preliminary results. We tried to redo this with a different lens setup and a different imaging setup a couple of weeks later, and same thing that Carl had said, we ended up with a bunch of extra frost on all of our samples that had accumulated over time. And so our pictures from that I didn't include in here are just covered in frost, which is very interesting as well. But with our current imaging plan that is being tested, the relative weight percent of water in these icy regolith is really difficult to determine. And that is very interesting planning going forward to these early Artemis missions, when this camera is likely going to be the only instrument that astronauts have in their hands as they plan for this. And trying to find focus on these dark regolith in these environments became very difficult, especially in the dark environments. And this is a repeatable experiment, but like I said, I think it needs to be done on a larger scale, potentially with more natural environments, so you can actually fill the entire frame of view of the camera and really start to test some of those other operational considerations. But through working with this, and from Zach has a presentation tomorrow, we've been able to have a lot of lessons learned that have gone forward and helped in the jet test that happened recently. We were able to take some of these lessons learned and adjust different imaging constraints and planning from within there. And so hopefully some of this will help us go forward. And so thank you very much.